Hello everyone, welcome back to Nated Engineering. Today we are doing Refrigeration Power Machines N6. Before we get deeper into the fundamentals of refrigeration, let's start by looking at few definitions. So we have heat. What is heat? We all know heat is a form of energy. That one we know. Heat is a form of energy which its flow is caused by temperature difference. So if we have 10 degrees Celsius, an object that has 10 degrees Celsius, and we have another object with 100 degrees Celsius, here there will be a transferring of heat energy. Where will be the heat energy going from to? It will always go from the object with a high temperature to the object with a lower temperature. Always heat will travel in that direction, from the high temperature object to the lower temperature object. And then we have number 2, which is cold. Cold is a relative term we use referring to the lack of heat in an object. If there is a lack of heat in an object, we say that object is cold. It's in a state of cold, or you can say it's just cold. And then we go to refrigeration. What is refrigeration? Refrigeration is the process of removing heat energy from an object. So if you're having an object which is, let's say, 10 degrees Celsius, and you are removing the heat energy up until maybe it gets to 4 degrees Celsius, we call this a refrigeration. You are constantly removing what? The heat energy from that object. And you know, as you're removing the heat energy from that object, the object will become what? Cold. Because we know cold is the relative term referring to the lack of heat energy in an object. So to remove heat energy in an object, we can use ice. If you take a bottle of soft drink, you put it into ice. Most of the time we put it into ice because we want it to be cold. And for it to be cold, we have to remove the heat energy that is contained within it. Therefore, we say refrigeration is taking place. We can also perform refrigeration by constantly passing a cold water or cold liquid around the body, and we know the heat energy will travel from the body which we want to refrigerate to the water that we're constantly passing around that body. So we can also use mechanical components to perform refrigeration because we want it to be sustainable. We know if we are using ice, sooner or later that ice will gain enough heat energy that will turn it back into water, which will after turn it into a vapor. So we want something sustainable. So that is when we introduce the mechanical components. These mechanical components, we utilize it for the purpose of transferring heat. We are going to call it mechanical refrigeration. Why? Because we are utilizing mechanical components to perform refrigeration. These are the components that we use in refrigeration. These are the main 4. We have the compressor, we have the condenser, we have the expansion valve, and we have the evaporator. These 4 arranged in a refrigeration system, we will be able to use them for the purpose of what? Transferring heat, or for the purpose of refrigeration. The refrigeration system will be arranged in this manner. First, we will have the compressor. And then after the compressor, we will have the condenser. Right after the condenser, we are going to have the expansion valve. Right after the expansion valve, we are going to have what? The evaporator. And then it's back to the compressor. These 4 will be joined together by a pipe or by tubes. And then we are going to have a liquid circulating around these four components. We call that liquid a refrigerant. A refrigerant is the one that is responsible for taking the heat energy where we want it to be absorbed to the place where we want it to be discharged. So a refrigerant is the one that will be transporting the heat around these four components. So this is what is going to happen. The heat energy will be transported from this, which is the evaporator, to this, which is the condenser. That's where the heat energy will be discharged. So we'll start here. We'll say this is 1, this is 2, this is 3, and this is 4. So what is going to happen is the refrigerant will come out of the evaporator because it entered the evaporator to absorb heat energy. It comes out of the evaporator as saturated vapor. So it will come out of the evaporator as saturated vapor. Why saturated vapor? Because it just absorbed the heat energy that we want to be absorbed from the evaporator. Now the temperature of the refrigerant has increased after passing to the evaporator. It comes out on the other side as saturated vapor. Now its temperature is also increased. So it's saturated vapor, high temperature. And then now we pass it into the compressor. We know the job of a compressor is to increase pressure. So when it passes through the compressor will raise its pressure. It will be high pressure. High pressure. And we know when pressure is increased, when we are compressing something, the temperature will also rise. So it becomes even higher temperature than it was in this state. It becomes a high pressure, high temperature refrigerant. Now we are having a refrigerant which is high pressure, high temperature. We pass it into the condenser. A condenser, that's where the heat energy is discharged. Remember, the heat energy is absorbed from the evaporator and discharged in the condenser. The condenser is something like this, and it is exposed to the atmosphere. Oh, sorry, I was not able. Yeah, now you can see. So yeah, as I was saying, the condenser is something like this, and it is exposed to the atmosphere. Or you can have water, cool water, passing through the condenser to absorb the heat energy from the refrigerant as it is passing through the condenser. So what is going to happen is, as the refrigerant is passing through the condenser, the heat energy from the refrigerant will be transferred to the water or to the air, that is the air of the surroundings. And then the refrigerant will come out on the other side as low temperature, high pressure. The pressure is not changing. Only the temperature will change since we just passed it through the condenser. It's high pressure. And then after passing it through the condenser, it will be low temperature and high pressure. We're now going to pass it through the expansion valve. So what the expansion valve will do to our refrigerant is that it will lower its pressure. It will have low pressure, and then we know that the boiling point of a liquid depends purely on the pressure that is applied within that liquid. When the boiling point of a liquid when the pressure increase, its boiling point will also increase. Now we are having pressure decreasing. As the result, the boiling point will also decrease. The refrigerant will start boiling, but that doesn't mean that the refrigerant is high temperature. It simply means now maybe you have decreased the pressure up until you got to the refrigerant having a boiling point of maybe 1 degrees Celsius. So this refrigerant is boiling, but it's still low temperature in such a way that if you pass it through the evaporator, it will be able to absorb heat from the product or from the object that we are trying to cool. Why? Because the object that we're trying to cool will be lower than, will have a temperature that is higher than the boiling point of the refrigerant at this stage. The fact that this is boiling doesn't mean that this has a lower temperature than this one. It simply means that the pressure here is lower in such a way that the boiling point maybe it's 1 degree Celsius. So as the refrigerant is passing through the evaporator, it will absorb the heat energy from the object, which will cause it to continue the phase change from the boiling point, since we know that when boiling point starts, we are now having wet steam. So absorbing the heat energy from the object that we want to cool will cause the refrigerant to continue that phase change up until it gets maybe to a state of where it is dry saturated or superheated, which are the conditions that you can have here. You can have this the refrigerant as wet steam. You can also have it as dry saturated. No, it's not wet. As dry saturated or as superheated. In fact, they will tell you about the condition of the steam. We are taking out heat from the evaporator, discharging it in the condenser, and as that process is being carried out over and over, the heat energy of the object that is in the evaporator will keep on decreasing. We are removing heat energy from the object. That what is refrigeration. So since we will be having the refrigerant evaporating from liquid, here it will be liquid, pure liquid, to it being steam. Starting from here, it will be wet steam up until it gets to a point where it's dry saturated or superheated. We have to know what formula to use when we are dealing with each type of steam. So we know H wet, which is wet steam. It's calculated using the formula HG, HF rather, plus X HFG. So whenever you are dealing with wet steam, this is the formula that you're going to use. Or you're going to use S wet, it's equals to SF plus X times SFG. That is the formula for wet steam. And then if you are dealing with superheated steam, is dominated by H soup. We're going to say H is given by HG plus CP, which is the specific heat capacity of the superheated steam. Let me just say soup, specific heat capacity of the superheated steam. And then we're going to say is T soup, which is the temperature of the superheated steam minus the saturation temperature. Hopefully you know these equations. And then we also have another one for this, which is S soup. It's equals to SG plus the specific heat capacity of superheated steam ln T soup. Sorry about that. Divided by TS. So these are the formulas that you are going to use whenever you are dealing with wet steam. This is the formula to use whenever you're dealing with wet steam, with superheated steam. These are the formulas that you are going to use. And whenever you are dealing with dry saturated is HG, and it is given by HF plus HFG. HFG, meaning SG will be given by SF plus SFG. These are the formulas that we will be using. These are the formulas that we will be using concerning the refrigerant as it is turning it to steam. As it is turned to steam. So we also have another formula which we call the ideal coefficient of performance. It is given by T1 divided by T1 minus T2. And then we have another one which is the actual coefficient of performance. It's given by the refrigerating effect divided by work done. Let's come back to our diagram. From this point to this point, the refrigerant is entering the evaporator, absorbing the heat energy from the evaporator. The object that we're trying to cool, remember, it's in the evaporator. The refrigeration effect is the heat energy that was absorbed as the refrigerant is passing through the evaporator. So the refrigeration effect, RE, we are going to say it is the heat energy at this point minus the heat energy at this point. We want to get the energy that was absorbed by the refrigerant as it was passing through the evaporator, and that will be H1 minus H4. And then we have work done. Work done, it's done by the compressor to the refrigerant. Therefore, it is equals to H2 minus H1. We are going to say work done, it's equals to H2 minus H1. So we can also say that the actual coefficient of performance, it's given by RE, which is H1 minus H4 divided by work done, which is H2 minus H1. That is what the coefficient, that is the formula for the actual coefficient of performance. You will always calculate for this one unless you are told to calculate for the ideal coefficient of performance. And one more thing, you must always know this is 1, this is 2. Always remember that S1, it's always the case where S1 it equals to S2. This one is very important. And then those are the things that those are the formulas that we are going to use in refrigeration. For this part, we are going to leave it here. I will see you on the next video.